lesson, we are going to look at how we can determine and analyze the acceleration of an object based on its velocity and position graphs. So specifically, we'll be looking at how to connect position and velocity to the acceleration of an object using position and velocity graphs, the topic for 1.3. So if we recall, an object that's accelerating can accelerate in three different ways: to speed up, slow down, or change direction. So in the case of one-dimensional motion, we can change direction, we can speed up, we can slow down. In fact, we've already seen each of these at play with our position versus time graphs and velocity versus time graphs before. We've seen that when objects speeding up, we've seen how our position versus time graphs look. The slopes get steeper. And we see how the velocity versus time graphs look. We move away from the 0 meters per second mark. While we're slowing down, we see the position versus time graphs, the slopes get less steep, and that our subsequent velocity versus time graphs head towards the 0 meters per second mark. So as a result, we've already seen cases where objects are accelerating from position versus time graphs and velocity versus time graphs. What we're now going to look at is how we can formalize these into some conditions in order to do a little bit more detailed analysis. So if we look at this velocity versus time graph right here, okay, again, we have an example here of an object that's moving in the rightward direction since the velocity is positive, and also an object that's speeding up since the curve is moving away from 0 meters per second. So if we want to determine the acceleration of an object at, say, 2 seconds from this velocity versus time graph, we use a principle that's similar from how we determine velocity from position versus time graph. Specifically, we calculate the slope of the velocity versus time graph as the slope represents the acceleration. The idea being is that in order to calculate the slope of this graph, we have to take our change in velocity and divide it by our change in time, our rise over run. But our change in velocity over change in time is also our acceleration, so the slope of velocity versus time graph is our acceleration. When the slope of velocity versus time graph is negative, the acceleration is negative, and when the slope of the velocity versus time graph is positive, the acceleration is positive as well. So let's look at an example here. Okay, so determining acceleration. Let's say we want to determine the acceleration at 2 seconds for an object traveling according to the above velocity versus time graph. So we calculate the slope of the line segment containing t equals 2. So we can use t equals 2 and the subsequent velocity equals 8 at 2 seconds. And then we can use any other point on our line segment in order to calculate the slope of this line segment and thus the acceleration at t equals 2 seconds. So if we use the other points, t equals 1, v equals 4, we'll have that our change in velocity is 8 minus 4, and we'll have our change in time is 2 minus 1. So as a result, our acceleration at t equals 2 seconds is going to be 4 meters per second squared. Hence, the principle is very similar to how to measure velocity from position versus time graphs. So now we're going to look at how we can determine the sign of acceleration using a position versus time graph. So we start off with some definitions from mathematics that are seen in calculus, although we won't be doing any equations with calculus. So a term from calculus that we use to describe the behavior graph is what we call concave up. Concave up describes when a graph curves or opens upward like the parabola that we have right here. Concave down refers to specifically when a graph curves or opens downward like we see our parabola doing right here. Okay? So if we look at the position versus time graph for an object that's slowing down in the leftward direction, changing direction and then speeding up in the rightward direction, we've seen in class that when we chart the subsequent velocity versus time graph, our velocity versus time graph will look like this right here. The object is heading towards the left in this region because the velocity is negative. It's slowing down because our curve is heading towards the 0 meters per second mark. And then after this time or dashed line right here, our object's now heading to the right because the velocity is positive, and we're speeding up because our curve is moving away from the 0 meters per second mark. What we can take note of right here is that when our graph is like this, for this very specific scenario, our graph is concave up for our position versus time graph, and the slope of our velocity versus time graph is positive. So when our position versus time graph is concave up, our acceleration, the slope of the velocity versus time graph, is going to be positive. Likewise, if we have a scenario where object is now heading to the right, slowing down, and then changing direction to speed up in the leftward direction. The velocity versus time graph, as we've seen in class, looks like this right here. Okay, we've seen that our object is heading to the right here because our velocity is positive, but slowing down because it's heading towards the 0 meters per second mark. And after this dashed line right here, our object is now changing direction and heading towards the left because our velocity is now negative, and it's speeding up because our object's heading away from the 0 meter per second mark. What we see right here is that the graph of the subsequent velocity versus time graph for this specific scenario is negative. The specific slope is negative right here. So what we can see right here is that for a specific scenario where our position versus time graph is concave down, the slope of the velocity versus time of the associated velocity versus time graph is negative, and hence the acceleration is negative for this specific scenario. So what we see here is when we're concave up, our acceleration is positive, and when our position versus time graph is concave down, our acceleration is negative. So we can formalize these observations into conditions for how to determine the sign of acceleration from a position versus time graph. So acceleration concavity. The acceleration, if the position versus time graph is concave up over a certain interval, the acceleration will be positive over that interval. While if our position versus time graph is concave down over a certain interval, the subsequent acceleration will be negative. As we've seen from our discussion right here. In fact, if you're in AP Calculus, you'll actually see why this occurs when we get to our unit on applications of differential calculus. So a nice little connection between acceleration concavity we've explored a little bit deeper in AP Calculus. So now we look at how to graph acceleration from velocity versus time. If we want to graph the the acceleration versus time graph for this velocity versus time graph, the principles we use are actually very much the same as how we plotted velocity versus time from a position versus time graph. We have to calculate the acceleration and hence the slope over each time interval shown, and then use that to graph our acceleration versus time graph. So for example, from 0 to 5 seconds, we can see that our velocity is constant and our slope is 0, hence our acceleration is 0 meters per second squared. From 5 to 15 seconds, we can see we have a positive slope and hence a positive acceleration. And if we calculate out that number specifically, we'll get that our acceleration is 1.6 meters per second squared. Lastly, from 15 to 20 seconds, we see that our acceleration is 0 again because our velocity is not changing. We have a 0 slope right here. So from 15 to 20 seconds, our acceleration is 0 meters per second squared. So now we can use these values right here in order to graph our acceleration versus time graph. Specifically from 0 to 5 seconds, our graph is at a acceleration value of 0. From 5 to 10 seconds, it's an acceleration value of 1.6 meters per second squared. And then from 15 to 20 seconds, it should say 15 to 20 right here, not 10 to 15. Our acceleration is again at 0, at an acceleration value of 0. And this is how we graph acceleration from velocity. So now if we want to graph velocity from acceleration, again, we use actually a similar procedure to how we calculate a change in position from a velocity versus time graph. So the idea here is the same principle, that the area between the acceleration versus time curve is actually representative of our change in velocity. The idea is that acceleration times change in time gives you your change in velocity, and acceleration is the height of our curve, whereas the change in time is the width of our curve. So acceleration times change in time, our change in velocity, is equal to the area between the acceleration curve and the time axis. So now what we can do is once we calculate this area, if we want to determine the final velocity over an interval, we add our area, our change in velocity, to the initial velocity at the beginning of the interval to find the final velocity at the end of the interval. Again, our final velocity is going to be equal to our initial velocity plus our change in velocity. Again, from algebra, we know that final equals initial plus change in the quantity. Okay. So we simply take the area that we find and we add it onto our initial value at the beginning of a time interval to find our final velocity at the end of the time interval. So let's see what this looks like in practice. For the graph at right, assume the initial velocity of the object is negative 4 meters per second. So what we're going to do here is we're going to analyze each interval and find the velocity at the end of each interval and then use that to graph our velocity versus time graph, the same way how we did this with graphing a position versus time graph from a velocity versus time graph. So for a time interval from 0 to 2 seconds, we can see that the area underneath our curve is 2 times 2, which is going to be 4. So our change in velocity from 0 to 2 seconds is 4 meters per second. So now we take this 4 meters per second, that's the area underneath this curve, and we add it onto our initial velocity, which is negative 4 meters per second, to get our velocity at the end of this interval from 0 to 2 seconds. So as a result, adding negative 4 meters per second with the area of 4 meters per second gives us a final velocity at the end of the 0 to 2 second interval of 0 meters per second. Now, this 0 meters per second is the final velocity at the end of the 0 to 2 second interval, and it's also going to be our initial velocity for the 2 to 4 second interval. So from 2 to 4 seconds, we see that the area beneath our curve is 0, so there's no change in velocity occurring, so hence our initial velocity at the beginning of the 2 second interval, which was again 0 meters per second, is going to be the same as our final velocity at the same of the 4 second interval, 2 to 4 second interval. Hence our final velocity at the end of the 2 to 4 second interval will be 0 meters per second, since we have no change in velocity occurring. Lastly, we see this 0 meters per second at the end of the 2 to 4 second interval is going to be our initial velocity of the 4 second to 2 second interval. So we can see that the area here is going to be negative 2 times 2 seconds, the 2 seconds from 4 to 6 seconds. So our area for 4 to 6 seconds is going to be negative 4, so our change in velocity is negative 4 meters per second. So we take this negative 4 meters per second and we add it onto our initial velocity for this interval, which is 0 meters per second, and that tells us that our final velocity at the end of the 4 to 6 second interval is going to be negative 4 meters per second. So now we can graph our velocity versus time graphs. We don't have to do motion analysis like speeding up or slowing down because we're not going to have any parabolic curves or anything like that like we see with position versus time graphs. We're going to have simply a connect the dot case. So we have negative 4 seconds to start. And at the end of 2 seconds, we have 0 meters per second. At the end of 4 seconds, we're moving at a velocity of 0 meters per second. And then at the end of 6 seconds, we're moving again with a velocity of negative 4 meters per second. Connecting the dots here gives us our velocity versus time graph from the acceleration versus time graph. And this is how we do an analysis of an acceleration of an object from position and velocity versus time graphs.